Good evening. It's Friday, the 18th of March, 2022, and this is the Randomizer. And for tonight, I'm Charles Schultz, your host, and we're going to be talking about Bernhard Riemann, the mathematician, tonight. And technically, his full name was Georg Friedrich Bernhard Riemann, and he was one of the most influential and fundamentally amazing mathematicians who lived from 1826 to 1866. He only lived 40 years, but he made some amazing contributions to mathematics, and we're going to get all into that in just a moment here. So go to universesciencecenter.com or schultzlaboratories.com. Click through the page, join us on the Randomizer every weekday at 6 p.m. Eastern Standard Time for a new random technical subject. So we talk about new matter every weekday at 6 p.m. And it's always something interesting or fascinating. You never know what you're going to learn or which direction the conversation is going to take. Come in live, ask your questions at our question and answer session at the end of the talk, and have some idea you want to share with us. Here's the time to do it. You're live on the chat when you join us. So also, Mondays, 9 p.m. Eastern Standard Time, we're starting up our lessons very soon, and it's a pretty close race between a robotics course and a course about math and music and sound. So we'll have that resolved very shortly. I will post the schedule for signing up for the classes on the Schultz Laboratories website very shortly. Please join us for that. It's a lot of fun too. It typically is 6 lessons of an hour plus a question and answer session at the end, and we cover all sorts of amazing subjects. Life in the universe, mathematics, robotics, electronics, the singularity, nanotechnology. You never know where it's going to go until you sign up for the class, and it's always going to be fun. If you are an educator or you have a skill that you wish to share with people, we encourage you to contact us, and we can set you up with a virtual world gallery from which you can teach your classes, share what you know with people, become an expert in what you're doing, share it with some people. This is a good way to get your word out and get some followers and share what you've learned in your lifetime with other people and see how it can benefit them. So join us as a supporter, as a member, or even as an educator. Join us at schultzlaboratories.com or universesciencecenter.com. Click right through. You can reach us many ways right there. You can even send an email to admin@schultzlaboratories.com. So we're going to get down to the subject matter of Bernhard Riemann now. Now, I know a lot of people are not greatly excited about the aspects of a mathematician's life. But you see, I've said this a number of times, and the language of the universe is mathematics. And this is one of the most important things to understand. I know a lot of people taking math in high school are like, if I got to take it to pass, then I'll do it. But they don't really see the beauty or the structure behind it. And this is a loss because there's so many things going on there, and I don't want to wax philosophical about it. But there are things in mathematics that should get you excited. And it's not just about counting pennies to make sure your checkbook balances. So let's talk a little bit about Bernhard Riemann. So being a mathematician, he was an analytical thinker. And some of the things that he contributed in the course of his lifetime, many people know about calculus. Well, he did the first rigorous analysis or formulation of the process of integration, the integral. And so people in calculus depend on a lot of his work for giving them a strict and solvable way of working on integrals. He also invented the Riemann integral, a specific instance. And yeah, absolutely, if you understand how integrals work, it's quite likely you're going to come up with one of your own, and a good reason for it. He also worked on something known as Fourier analysis, the Fourier series. Fourier was another mathematician, and one of the things he was focused on was the ability to take a signal, a complex signal, and break it down to its components. Now, what would that be like? How does it make sense? Imagine you went out to a restaurant and you had a wonderful meal, and you took a sample of that meal and you put it in a special analyzer that would crank out the recipe, what its components were and how much of each. The recipe to create that meal. Well, Fourier analysis and the Fourier series that Riemann worked on is such a device. You can put a complicated signal into the Fourier analysis process and it will spit out what it's made of. So in essence, you can take this complex waveform and it will tell you what the fundamental frequency, what the harmonics, and what the values of each are to create that waveform. It gives you the recipe so you can recreate it on demand. And that's a really amazing piece of, call it retro engineering. And why is it important? Well, you can imagine the mathematics involved in taking a body scan or a CAT scan or an MRI scan and getting all the layers of the image worked out. How do they know? I mean, you've got a little sensor going around the body like this, scanning you. What is it doing? What it's doing is it's doing Fourier analysis of the data that has been recorded by the sensors. And mathematically, it's working backwards to what shape and density it took to create that complicated jumbled up signal. It's pretty amazing. It's very similar to what happens when a bat is hearing a sonar signal and figuring it out, or a dolphin. It has its roots in the same sort of process. And so Riemann spent a lot of time working on the Fourier series and got a lot of headway. I think that's probably the best way to describe that phase of his work. What's interesting is he also worked in higher geometries. We all think of 2 or 3 dimensions. He worked in 4 dimensions and more. And a lot of mathematicians did because it was sort of uncharted territory at the time, particularly in the 1700s and 1800s. Riemann was famous in one respect for being able to prove that he could map one surface onto another. And why is this important? If you look at a ball in a computer graphic, it has a texture wrapped on it. And how is that transformed? I mean, they start with a flat picture. How does it get wrapped onto the ball accurately? This is called a mapping and a geometric mapping. So imagine taking a ball and somehow mathematically splitting it into slices and laying it out on a plane so that you get a beautiful recreation of the surface of that thing with little or no error. That's a mapping. Now, what Riemann did was he also was able to prove that certain surfaces were actually equivalent to one another. For instance, the surface of a plane is the same as the surface of a cylinder. You can literally unwrap a cylinder onto a plane, and the amount of curvature and type of curvature is identical. So he brought us a lot of very powerful mathematical transformation and analysis tools. So one of the things that he's well known for is called the Riemann zeta function and the Riemann hypothesis. They're tied together. The zeta function goes back to complex numbers. One of the things I discussed a couple of nights back, where you have an imaginary value and a real number stuck together. A complex number has a real part, which is like 7 or 41 or 9.6, and added to it is some amount of the square root of -1, the imaginary unit. So when you put those two together, you get a complex number. So what's special about a complex number? It shows a 1 point on the x and y graph. It pins it down for you exactly. But what's interesting is he worked on this zeta function. So the zeta function takes a complex number as an input, and then it does some crunchy, mathematical stuff. It spits out an answer. All right, so this function is a series of numbers that get added together. It's an integral, and the complex part that goes in can be any number at all except 1. Now, here's the cool part. He formulated his hypothesis. He knew that there were certain places where the answer would be 0, and they were trivial zeros. So anywhere that the real part of the number was a negative even number, like -2, -4, -6, -8, you would get a 0. Those are trivial zeros. But then he noticed that other zeros would crop up, and in that case, the real part would always be 1/2 plus some imaginary part as well. So he came up with this theory that said all of the non-trivial zeros will always be on a 1/2 plus some imaginary number. Now, why is this important? This is one of those math problems that you look at it and you go, well, it's probably true, but we can't prove that it's true, and we can't prove that it's false. And understand something about logic and mathematics. If you can prove a thing to be true, that's great. Or if you can prove a thing to be false, that's great. You've got a definite answer. Sometimes you can't find a proof of it being true, but you can prove that the proof of it being false is wrong. You can sometimes prove that it cannot be false, and therefore, by extension, it must be true. And it sounds like waffling, but it really isn't. It's kind of like you have one sock you can't find, and you've only got one cabinet, and you know it's not on these drawers. It's got to be in the other drawer. It's sort of like that, only a little more solid. Numbers don't vanish in the dryer like a sock might. But the whole point here is mathematics and logic have very rigorous rules. And in most circumstances, you can find a proof for a thing being true or false. One of the things that's been realized is mathematics is incomplete. And as a result, there are some things that are true, but it's not possible to find a proof for them. And some things we know are false, but it's not possible to find a proof of that either. So in some cases, we're always off in la-la land. Well, the Riemann hypothesis is one of those sorts of things where it would be great to know if it's true because it's related to such things as the prime number, the prime counting function. And if you could prove it, then there would be implications in other branches of math and other functions. So let me give you an example of a simpler thing that's easier to understand for people. It's called the Goldbach conjecture. In the Goldbach conjecture, it's said that any even number is the sum of two prime numbers except for the number 2, because 2 is a prime and it's even, so you don't count number 2. But any even number is the sum of two primes. That sounds perfectly reasonable, but how do we know it's true? We have tried billions and trillions, literally, of these numbers on computers, and nobody has ever found a counterexample. So we have not been able to prove it false, because if we could find one counterexample, we know that it wasn't false. But we also have not been able to find a direct logical proof that it is true. It probably is. We expect that it's true. But how do you prove it? So the Goldbach conjecture is one of those problems. So this is such an important problem. There is a list of 23 unsolved problems in math. And the Riemann hypothesis, along with the Goldbach conjecture and the twin prime conjecture, are problem number 8. And what's significant with these problems is they're considered so difficult to prove that there is literally $1 million prize on their head. So if you happened to figure out the answers to these problems with a proof, you'd win $1 million. That's kind of interesting. And you wouldn't think that that sort of excitement could exist in the dry, passionless world of mathematical functions. But the fact is, it does. Mathematics is fascinating stuff, and I have to admit, I get excited about a mathematical problem. And things like the Riemann zeta function, I love it. You know, it's one of those amazing, simple functions that gives you an answer, and he's probably right about where those answers lie. We have no clue how to prove or disprove his statement. So problem number 8 on the list, if you solve it, you got $1 million right there. Of course, it might not go as far today as it would 50 or 60 years ago, but that doesn't matter. I think a lot of people would be happy just the same. So other non-trivial problems. Okay, I have one that I absolutely love, and you'll probably end up playing with this when I describe it to you. There is something where you take a number, and if it's even, you divide by 2, and if it's odd, you multiply by 3 and add 1, and you get a new number out of it. Now, in this problem, you put a number in and it goes up and down and up and down, but at the end it always ends up going down to 4 and then 2 and then 1, which, by the way, brings you back to 4, 2, 1. So there's a little loop at the bottom of this. This amazing, they sometimes call them snowflake numbers. And it's, I think it's one of my favorite mathematical problems. So here's the question. We know that any number can be put in, and it may rise and fall all over the place, hence the name snowflake. They move just like snowflakes do in a cloud. That's interesting, but the most interesting thing is there a number that never reaches the 4-2-1 cycle? Is there a number that somehow remains up here in the stratosphere somewhere, circling around in its own loop that doesn't terminate at the bottom? Nobody knows. And there doesn't seem to be any counterproof, any examples of one that exists. And on this front, people have literally run computers through trillions and literally quadrillions of numbers, and nobody has yet found a counterexample. It appears that this tree of numbers goes on and contains every number, and they all end up going to the bottom of the list somewhere. So the problem here is there is no proof. So that's one of the most fascinating, simple problems in mathematics. And I think that if you stop and think about it, that's one of those things you're going to scribble some notes somewhere, put in number 7. Okay, it's odd. So that 3 times that is 21, add 1 is 22. Then it becomes, oh, it's even, you divide, then it's 11. Then it becomes 34, then it becomes 17, then it becomes 52, then it becomes 26, and it goes up and down all over the place before it reaches the bottom. It's kind of a fun problem, so you might want to play with that a little. So anyway, back to Bernhard Riemann. I have to say, a lot of the things that I do depend on his analysis, and I use his functions and, well, I mean, use calculus, you're using some of it. Definitely one of my favorite mathematicians, and I would recommend reading a little of his work if you are of a mathematical bent. So anyway, I'm going to also encourage you to go to the Universe Science Center or schultzlaboratories.com, sign up, become a member, join our lessons, have fun with it, share it with your friends, walk around in our galleries and experience our 3D interactive exhibits. They're just amazing. And share it with your friends. I said, get some kids in there. If you have time, some people, older people who don't play games, who aren't gamers, may sometimes have some frustration with navigating. There is a tutorial on the site, and if that doesn't work, get an 8-year-old. They'll show you what to do. They know everything about games. So that being said, it's time for my quote for the day. And this is a good Friday for this. Seek the Lord and his strength, seek his face evermore. And that's 1 Chronicles 16:11. You can't go wrong if you're dealing with the guy who built the universe, right? I read the book and we come out ahead. Don't be faint of heart. It's all good. So everybody have a wonderful weekend. Look up Bernhard Riemann and his mathematics and the Riemann conjecture, his hypothesis, and enjoy your weekend. I hope that everybody has a wonderful time and take these things to heart and make the world a better place. We all will appreciate it. Thank you and have a wonderful weekend. Goodbye.